Hi, today I'll introduce Ampere's law to all you viewers in a very brief video, more of a brief introduction. The effects behind the law were discovered by a French physicist named André-Marie Ampere in 1826 while he was giving a lecture. The main thing you can take away from the law is that current generates a magnetic field. Or that current is proportional to the magnetic field. So maybe if you double the current, you'll double the magnetic field, stuff like that. Okay, so while there are other laws that say basically the same thing as Ampere's law is the one used most often conventionally. So I will be showing you the Ampere's law in the case of infinitely long wires. So let's draw our wire. Here's our infinitely long wire. I, that stands for current. And now we want to figure out where the magnetic field is. So Ampere's law says, in the case of infinitely long wires, that the magnetic field circulates around the current. To get a sense of where the circulation of the wire, of the magnetic field around the wire is, grab the wire with your hand. So put it like this, and then point your thumb in the direction of the current. I should probably do this with my right hand. And now you curl your fingers around naturally, and then that shows you the direction of where the magnetic field will be. So now let me draw this. Keep in mind that circles means that's where the field is coming out of the page, and then X's are where they go into the page. So you will just end up having a bunch of these all around. I'll just draw a few. So the arrow shows us the direction it's going in. The X means it's going into the page, so then it loops around, and then it comes back, and then it comes out of the page again with those dots, and it just goes around the whole wire like that. Alright, maybe to better explain that, let me use my pen. Alright, so we have my pen. We'll pretend that this is the infinitely long wire. The current is going in this direction. So I grab the pen naturally, and then I point my thumb in the direction of the current. So I said that I was going upwards, so I point it like this, and then I curl my fingers around so I know that the current is going to go around my pen like this. Alright, now let me show another way to do this. Okay, so let's pretend that this dot is the wire coming out of the page, and the current is going through in this direction as well, just like I was showing with my pen. So now, where would the magnetic field be going? Well, as I just showed, it would be going around. So it would look like this. That's what it would look like if you were on the other side of the facing the wire. So what does that look like? That looks like a circle. So now let's try to figure out what the equation is. Well, I already know that the equation, based on what Ampere said, is integral of B. B stands for the magnitude of the magnetic field times times dl, and I know this is equal to sorry, my pen's running out. Mu naught times I. Like I said, I is current. Mu naught is called the permeability of free space. It's just a constant, and this is equal to 4 pi times 10 to the negative 7 times Tesla meters per ampere. Alright, back to the circle and this part. We can, in the case of infinitely long wires, since I showed that this is a circle, we can simplify this to be times 2 pi r, and that will be equal to what was written up here, because what is the circumference of a circle? 2 pi r. And then we just multiply by b, which will be a constant in the case of infinitely long wires. No matter where you are on the wire, considering the current will be constant throughout the wire. Okay, so now that we've established what Ampere's law is, so B, and then we can simplify this further. This is how we normally express it in infinitely long wires. The magnitude of the magnetic field is equal to the permeability of free space, or mu naught, times the current over 2 pi r. Now, let's do an example. Let's say we have a wire, okay, and we're putting the current will be equal to 5 amps. Alright? And we'll say that we want to find the strength of the magnetic field 1 centimeter away from the wire. So now let's use our equation. So B is equal to mu naught, which is a constant, which I wrote up here, times I over 2 pi r. So B is equal to 4 pi times 10 to the negative 7 times 5 amps. I'll just leave out units for now. Over 2 pi. Wait a second. We want the units to cancel out nicely, so we just get Teslas for B, because that's what the magnitude of magnetic field is measured in Teslas. But mu naught is measured in Teslas meters per amperes. I'm given centimeters, so I need to multiply the centimeters by 10 to the negative 2 to get them in meters. So I'll have times 0.01 meters. Alright, so now let's simplify this further. So we can cancel out the divide 2 pi by 4 pi, and we're left with 2 times 10 to the negative 7, but the 0.01 is really 10 to the negative 2, so we can rewrite this as 10 to the negative 5 times 5. So we have B is equal to 10 times 10 to the negative 5. B is equal to 1.0 times 10 to the negative 4 Tesla. Thank you for watching the video. If you have any questions, please leave your comments below. This is just a brief overview, and I'll be releasing more videos soon. Thank you for watching.